Fundamental theorem of orthogonality. Fundamental theorem of orthogonality states that the row space is orthogonal to null space in Rn. The row space is orthogonal to null space in Rn, and even the column space is orthogonal to left null space in Rn. The meaning is row space. We can consider a matrix A or any other one. The row space is orthogonal to null space. Means if the matrix A is considered, then its row space would be the number of rows, how many are there in that one. And the number of rows would be m in number. These m rows, when they are multiplied with the null space, means row space is orthogonal to null space. So we know what is the null space. The null space means A into x is equal to 0, means whatever the values of these x unknowns are there, depending upon the matrix length, depending upon m and n values of this matrix. So by n only, means if it has m number of rows and n number of columns, then these values, the number of unknowns should be n. So these n number of unknowns are orthogonal to the row space. Row space is orthogonal to null space in Rn. Certainly, as the null space means row space, by default while finding x is equal to 0, we multiply each of the row with the columns and the result would be 0. Means by default this row and this column are orthogonal to each other. That is the meaning. So by the null space itself, this definition is true. Like when each of this row is getting multiplied with this column, will get the 0 result. Hence these two are orthogonal to each other. And the orthogonal to null space, of course, it has to be having n number of elements if this A is m into n. Then the column space. The column space means it will be the columns. The column space is orthogonal to. Now let's see, these columns, are they get multiplied with this? No, they are not going to get multiplied. The rows get multiplied with these, but these columns, if we need to find the column space, the orthogonal value of this orthogonal to this column spaces, then as these are columns, we should have a row on this side. Means if this is A, for this A will be having the number of columns whatever they may be. Let's say the column elements are there in this way. If they all have to be multiplied, we may have any number of columns. It is, let's say, m into n order matrix. Then if these columns are to be multiplied, then certainly we should have a row here. We should have a row here having some number of elements. And if the number of elements, if the number of rows here, the number of rows is m, certainly we should have m. Let's say this is y1, y2 and so on, up to how many? It should be ym. So ym into ym into this last, let's say it is a11, so it would be a m1. So these get multiplied. Means the column space, the orthogonal value, the orthogonal space for the column matrix, for this column has to be the left null space. Means when this gets multiplied with this column, we should generate 0, so which will be referred as the left null space. The column space is orthogonal to left null space in Rm. Rm indicates the number of elements. The number of elements here have to be it is am. So they have to be m in number because number of rows. And to prove that one, let's see what is the thing followed. Suppose x is a vector in the null space. Let's consider x as a vector, and then ax has to be 0 when each of this row multiplied with this column has to give 0 as per the orthogonality principle, because x transpose y has to be 0 by that rule. So, and here the system has m equations because m number of rows are there, so which will be written as row 1 multiplied with all these elements should lead to 0. Similarly, row 2 multiplied with these all values of x has to give 0. Similarly, the last one. So that clearly shows that the row space is orthogonal to the null space, because null space is the space by multiplying that one with the matrix will get always the 0 as our result. So left null space is orthogonal to our matrix, we can see, or the row space is orthogonal to the null space in R. And similarly, we can go for proving the other. So the next one is this one. This other definition is for this one. The column space is orthogonal to the left null space. To understand that, we know that A transpose Y is 0 and Y transpose A is 0. For that, now as shown here, the column has to be multiplied. Now column 1, column 2, column like this, n columns would be there. And to get multiplied with this column, we should have the transpose. So we should have y1, y2 up till yn, and when this y transpose gets multiplied with this column, will generate 0, and certainly to this A it has to be the left null. Means this y has to be the null space. So the left null space is as given by the column space is orthogonal to the left null space. Means it has to be on the left side, otherwise it won't get multiplied. It's the meaning, and this is one of the important theorem in this orthogonality. And certainly the column space is orthogonal to the left null space, which will be represented as NAT, perpendicular to the column space, and on the other side it would be the null space is orthogonal to the row space, because we have the habit of representing the column space, transpose of column space is nothing but row space. And we are understanding that one with an example. Consider the matrix. Let's say this matrix is A, having this all rows. Now we can see it has 3 rows and 2 columns. The rank of this matrix is what? And it's clear here that 1, 3, 2, 6, 3, 9. The second row is the multiple of first row by 2, and third row is the multiple of the first one by 3. Means when we multiply this one by 3, we'll get this third row. Suppose, then what is the rank of this? The rank has to be, because when we go for the pure generation and obtaining the reduced matrix, we can make these all zeros. Only one row exists. So let's understand this one, the spaces, the null spaces. What can be the null space for this one? Before that, what is the basis of this? The basis, the row basis. The rows are multiples of 1 and 3. So the basis, the row basis for this matrix is 1 and 3. This is the row basis. And from this, if 1, 3 is getting multiplied with 3 minus 1, will generate the 3 and minus 3, which will make it as 0. Similarly, if we can take the multiples of this or we can have the multiples of this. The result would be 0. Even though this 1 3 is 2 3 also, instead of 1 3, if we have 2 6 also, then also the result would be 0, even though it can be any multiple of this 1 3, will get the result as a 0. So these are the bases. So 1 3 is the basis of this matrix, and the rank of this matrix is 1. So 3 minus 1, even it can be any multiple of 3 minus 1, means it can be even. If this gets multiplied by 2, 6 and minus 2, if it is, then also will get 0, because this will be 6 and this would be minus 2. 3 into 2, it would be minus 6 with a minus sign. So the same applies. Now what is the thing we need to understand is the rank of the matrix is 1, and this is the basis. As these all are multiples, the second row and third row are the multiples of the first one. If we can make up this first row as a 0 by multiplying some column, by taking some unknown space, then that same will make the other rows also 0. And even the next thing is, even though that null space is getting multiplied with any of the scalar quantity, even that forms the null space for this matrix. The next one is regarding, we consider a subspace V. Let's say V is a subspace. Let's say it is n-dimensional. Then the subspace of all vectors orthogonal to V, means there can be one more subspace, all vectors orthogonal to V is called the orthogonal component of V. It is denoted by V perpendicular, V perpendicular. We can write V perpendicular in this way or in this way. Then the fundamental theorem of linear algebra says that the null space is orthogonal component of row space in Rn. That is always true. The left null space is orthogonal component of column space Rn. For Ax is equal to B, it requires the B to be perpendicular to the left null space. Ax is equal to B is solvable if and only if YTB is equal to 0. So whenever Y transpose A is equal to 0, then only it becomes solvable, otherwise no. The meaning is, let Y transpose A is equal to 0 means this Y transpose is a row matrix, and this row matrix is orthogonal to A, and this Y transpose should be even orthogonal to this B. The meaning of this one is X is equal to B requires B to be perpendicular to the left null space. Then left null space of A is YT, and this YT should be perpendicular to the left null space, and that is YT of A, left null space. YT is left null space and it has to be perpendicular to B. Now here we understand little bit regarding the subspaces. Let V and W are the complements of each other. V and W can be orthogonal without being complements. So their dimensions can be too small. And let's consider this one. The line V spanned by 0 1 0 is orthogonal to the line W spanned by 0 0 1. Now here we can see this, what is complement and all. Let's consider W, V and W. Now V is this line, and as it says, the line V is spanned by 0 1 0. Now it is a three-dimensional coordinate system. In three-dimensional coordinate system, we know X is in this way, Y and Z. And if we are representing the point 1, 0, 0, it will be here. Represent 1, 0, 0 at this place, and let's say it is a unit dimension. Then if we are representing, now it's our x-axis, it's our y-axis, and if we are representing y is middle, 0, 1, 0 would be the point. And if we are representing the point on the z-axis, it has to be represented as 0, 0, 1. Let's say this point it is. Now the point 1, 1, 0, point 1, 0, 0 is on the x-axis, it is on y, it's on z. Because in three-dimensional coordinate system, every point is represented by x, y and z. The first one is always x, second is y, and third is z. Now the meaning of that one is, there is a line, there is a line spanned by 0, 1, 0, means this line it is, 0, 1, 0. The V spanned by 0, 1, 0 is orthogonal to the line W spanned by 0, 0, 1. 0, 0, 1 would be this way, 0, 0, 1 would be along the vertical axis. It runs in this way, of course straight line it is. And now we can see this one is our V and this is W, and this V and W are normal to each other, they are orthogonal, but they are not complements of each other. Usually there is a thing that if the two vectors are complements of each other, they can be the orthogonal ones. Means if 0, 1, 0 is there, then it can have its orthogonal as 1, 0, 1. Sometimes we say these are the complements. This one and these two are complements of each other. Now what about their orthogonality? So we are studying even they both are not orthogonal to, like they are not complements of each other. Means this 0, 1, 0 is not equal to, certainly it is not equal to 0, 0, 1. 0, 0, 1 is different because its complement is different. Even though they are not complements of each other, they are orthogonal, is the meaning of that line. Here the orthogonal component of W is two-dimensional plane. The W is two-dimensional plane, the orthogonal component of W. The orthogonal component means when we take up the complement of this W, it is 1, 1, 0. This 1, 1, 0 means it would be 1 in x and 1 in y. So it would be a plane in this way, 1, 1. This represents the point 1, 1 because x is 1, y is 1, 1, 1. So 1, 1, 0 is the plane. Here V is a part because when we say this plane, V was this line 0, 1, 0. It is a part of this plane, and V and W are perpendicular to each other. Now the thing is, this W is 0, 0, 1 and its complement is 1, 1, 0, which is represented by a plane. Now we can see that this W and this plane, which is W perpendicular, this W and W perpendicular, this plane are even perpendicular to each other. Means whenever we go for finding the complements, when we find the complement of a vector, that complemented form is always perpendicular to the original one. And even sometimes if we are taking the axis like y and z, they are also perpendicular, even they are not complements of each other. That is being indicated here. And here we can see W and V are perpendicular to each other, and here this line is W and this plane is 0, 0, 1 is W, and the complement of that one is 1, 1, 0. So this plane and even this W and this plane are perpendicular to each other. That is orthogonal complements. V is equal to W perpendicular. So this is regarding the orthogonality.